Good afternoon. Uh, Good afternoon. We start with our last session of the day. This is essentially a tutorial and question answer session on the topic dynamics of Invicid flows. We have organized the session in the following way. First, our teaching assistant Mr. Aditya Bandyopadhyay will discuss about the tutorial problems and the solution keys. He will not solve the problems completely, but he will discuss about the like hints or keys towards solving the problem. And after that we will take question answers. Myself and Professor Ghosh Maulik will respond to the questions from the various centers, and that is the agenda of this session. So, I hand it over now to Aditya Bandyopadhyay.
So, good evening everyone. So, the first question today pertains to the applicability of the Bernoulli's equation for this given flow field. So, it is given that the velocity components in an Invicid constant density steady flow field are as follows. The u velocity is a constant a by 2 times x plus y plus z. The v velocity is a by 2 times x plus y plus z, and the w component of the velocity is minus a times x plus y plus z. Now, we consider a directed line segment So, we consider a directed line segment from the point 0 0 0 to 3 comma 3 comma 0. Now, it is given that the pressure is 0 gauge at the origin. So, the first question is, can the Bernoulli's equation be applied to find the change in pressure experienced So, the question is whether the Bernoulli's equation can be applied to find the change in pressure experienced on moving from point P to Q along the direction PQ. So, we have a line vector PQ which points in this direction. So, the first task will be to evaluate what the dl vector is. Now, if you remember, the applicability of the Bernoulli's theorem depends upon whether or not this term is 0 or not. So, you have the velocity field which is so given this velocity field, you must now determine whether or not this term is 0 or not. So, from the data in the problem, you need to find out whether or not you can apply Bernoulli's theorem to find out dP between points P and Q. It is straightforward calculation which you should be able to do on your own. Now, the second part is starting from the Euler's equation of motion in the differential form, we need to find out the pressure at point Q. We also need to find out the stagnation pressure at the same point. Now, this is a fairly straightforward question in which you need to start from the basics. So, you need to follow the derivations which Professor Chakravarti had done, and after this you need to find out what the pressure at point Q is. Note that the pressure at point P is given as 0 gauge. So, we will move on to the next question. So, a rectangular chip floats on the top of a thin layer of air. So, the hatched thing that you see in the diagram is a rectangular chip. This is a plate and there is air blowing in from the bottom. It is given that the final condition is steady, the flow is inviscid, it has a constant density. So, we need to find out what weight of the chip can this flow sustain. Now, we can assume that the width of the chip is infinite into the paper, which means the problem is essentially two dimensional. So, first of all you need to find out what the flow field will look like in order to evaluate the pressure distribution on the bottom surface of the chip. After evaluating the pressure distribution on the chip, that can be integrated over the area to find out the force acting on it, which will be balanced by the weight of the chip. So, it is given that there is uniform blowing through the bottom, which is say V naught. So, if you take a control volume as shown in the figure, you can find out by conservation of mass what the u velocity is. So, say I have taken the length of the control volume to be x and the height of the gap is h. So, for this conservation of mass will yield V naught times x is equal to h times u. So, through this we can relate u as a function of x. In order to find out what the velocity distribution for the v component is, we can make use of the continuity equation. Since the flow is considered to be incompressible. Now, you can integrate this once and use the appropriate boundary condition that there is no penetration on the top wall, that is at y equal to h, v is equal to 0, no penetration. Having done this, we would obtain the velocity field. Now, we will use Euler's equations to evaluate the pressure field. So, we have obtained u and v as a function of x and y. Now, we need to find out what p is. So, rho into Ax is equal to minus del p del x, rho into Ay is equal to minus del p del y minus rho times g. Now, Ax and Ay are to be found out by using the flow field. For a steady flow, Ax is this, for a steady field this will be 0. Now, these two you can evaluate using the information that you had just obtained. Similarly, you will obtain what Ay is. From that you will integrate this equation once to find out p and to find out the constant you will make use of this condition, this equation. Once the pressure field is found out, you need to integrate it over the area of the chip and then balance it by the weight. So, for the chip, the net force because of the pressure is equal to the mass of the chip times the gravity. So, by this methodology we can find out how much weight this blowing in stream of air can support. We move on to the third question, which pertains to flow measurements. So, pitot tube is inserted in an airflow at STP to measure the flow speed. The tube is inserted so that it points upstream into the flow, and the pressure sensed by the tube is the stagnation pressure. The static pressure is measured at the same location in the flow using a wall pressure tap. If the pressure difference is 30 millimeter of mercury, determine the flow speed. The specific gravity of mercury is 13.6, this density of water is 1000 kg per meter cube, and the density of air at STP is 1.23 kg per meter cube. So, this is a very routine problem which Professor Ghosh Malik had gone through. So, air is flowing in this pipe and we have this pitot tube facing upstream, and we have the static pressure tap which is flush on the surface. So, the point A is able to measure the stagnation pressure and point B is able to measure the static pressure. Now, if you would remember Professor Ghosh Malik's derivation on how to find out the differences between the pressure, you can find out that P A is equal to P B plus half rho V average square. This rho is of rho air, and P A minus P B is given as 30 millimeter of mercury. So, by this one can easily find out what the flow velocity is. If there is any doubt, you can always go through derivation that Professor Ghosh Malik had shown, and this is a pretty straightforward problem. The final problem is that of a venturimeter consisting of a converging portion followed by a throat portion of constant diameter and then a diverging section. This is used to measure the rate of flow in a pipe. The diameter of the pipe at section 1, which is upstream, is 15 centimeter, and the diameter at section 2, which is the throat section, is 10 centimeter. We have to find out the volume flow rate when oil is flowing through the system. The pressure difference between points 1 and 2 is 20 kilopascal. even this the concepts pertaining to this problem were clearly done in the derivations in class. Still for completeness I will just discuss about the methodology to solve this problem. So, you have two sections 1 and 2. The section 1 is upstream of the throat and section 2 is the throat, and the diameter of the section at the throat is 10 centimeter, whereas the diameter upstream is 15 centimeter. Now, we can apply Bernoulli's equation along a streamline, the red line, and relate the pressure and velocity at sections 1 and 2 respectively, the average velocities at 1 and 2 respectively. It is given that P1 minus P2 is 20 kilopascal, and we have to make use of the fact that since the flow is of constant density, A1 into V1 is equal to A2 into V2, where A1 is pi d1 square by 4 and A2 is pi d2 square by 4. So, by relating the velocities at the sections and by making use of Bernoulli's equation, we can find out what the velocity is, and consequently we can find out what the volume flow rate is by multiplying the volume the velocity by the area of the cross section. So, you should solve the problems and submit it to your coordinator. The answers will be uploaded later on, which will then be evaluated. Now, we move on to the question answer section, which will be answered by Professor Chakraborty and Ghoshmali respectively. One three one four.
1314. Next. 1310.
Hello.
Yeah.
Hello, sir.
Yes. Hello.
Am I audible?
Yes, you are audible.
Hello, sir.
Hello.
Sir, my question is, can we apply Bernoulli equation to a siphon? Yes, sir. Sir, can we apply the Bernoulli equation to a siphon?
Siphon.
Sir, my question
Okay,
is,
okay.
can we apply Bernoulli equation to a siphon?
Yes. I have got your point. So,
Yes, sir.
there are three restrictions, three important, not three restrictions, there is one important condition, that is V cross omega dot
Yes,
dl. So, let me write it again. So, for the Bernoulli's equation to be applicable, in addition to steady flow, you have to make sure that this particular term is 0 in the derivation. So, we discussed three cases in which that becomes possible. One is that the your evaluation, your assessment is along a streamline, so that dl is oriented along a streamline, because V is also tangential to the streamline and dl is also oriented along the streamline. This vector operation will give you 0. So, in that case this becomes 0. So, the first case is along a streamline. So, in the siphon if you consider a streamline, you can apply the Bernoulli's equation between 2 points, provided you model the flow, you can model the flow as Invicid, constant density flow or the flow of an incompressible fluid and steady flow and along a streamline. Otherwise there are several other conditions in which you can apply. For example, if the vorticity is a null vector, that means it is irrotational flow, then you can apply between any 2 points, but in the siphon usually the Bernoulli's equation is applied between 2 points along a streamline, therefore this restriction is not necessary. And the third restriction, which is not very common, but if you have V cross omega perpendicular to dl, if you choose your line element dl in such a way that V cross omega is perpendicular to that, then also this term becomes 0. So, for siphon, if you look into the textbooks where the problems on siphon are solved, the points, various points are located along streamline, along the same streamline. So, if they are taken along the same streamline, you can apply Bernoulli's equation provided the inviscid, steady and incompressible fluid condition is satisfied. Okay. Okay, thank you. One one zero three. Yeah, good afternoon.
Yes, sir. My question was related to the Reynolds transportation theorem, which we have covered in the last session.
Reynolds transport theorem tutorial will be covered tomorrow. This tutorial is for dynamics of inviscid flows. So, if you are having any question on dynamics of inviscid flows, you can answer. I mean we will be happy to answer.
Thank you, sir. My question was related to the Reynolds transportation theorem only.
Okay, so you defer your question to tomorrow. 1316. 1316.
Hello, sir.
Hello.
Hello, sir.
Hello.
Hello. Am I audible?
Yes, you are audible.
Sir, good afternoon. My question is on Bernoulli's equation. This popular Bernoulli's equation V square upon 2 plus P upon rho plus Vz equal to constant is applicable or valid for steady flow or incompressible ideal flow along a streamline. But in practice, like in our lab, in case of pipe flow, we apply this Bernoulli's theorem, and how much variation is expected between ideal and actual condition. That is what I wanted.
Okay, let me answer your question. This is a very important question and let us address it carefully. The equation that we apply for pipe flow is not actually Bernoulli's equation. It is misnomerly known as modified Bernoulli's equation, but it is actually an energy equation integrated over cross section. So, if we write, so if you have a pipe, I am trying to sketch a pipe, I believe this image will come now and you will see. Yes. So, you have a section 1 and a section 2. So, you have P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus some head loss. I will come into the physical significance of this, but first most importantly the velocity is V1 square and V2 square, they refer to velocities, average velocities at sections 1 and 2, that is the first point. average velocities, not velocity at points 1 and 2 which are there in the Bernoulli's equation, but the Bernoulli's equation is applied between 2 points. Here the equation is applied between 2 sections, so V1 and V2 are average velocities. Now by these 2 terms we are essentially trying to represent the kinetic energy, but with the average velocity it may not be accurate to represent the kinetic energy. The average velocity will represent the kinetic energy of the section when the velocity profile is uniform, which is maybe very closely true for turbulent flow, which we will discuss later on. But for laminar flow there is a significant difference between velocities between points, so because the velocity profile itself is parabolic. So to take care of the velocity profile you multiply with correction factors alpha 1 and alpha 2 which are called as kinetic energy correction factors. These correction factors are there so that even with the average velocity of the sections we are able to represent the kinetic energy. So the first point is that we do not have we are not applying the Bernoulli's equation between points 1 and 2, rather we are writing the energy conservation between sections 1 and 2. To write the energy conservation we have a term HF which is positive, which is called as head loss. So this, well, I mean, what is the origin of this head loss? Because of viscous effects in the flow there is irreversible conversion of mechanical energy into intermolecular form of energy. So because of this irreversible conversion of mechanical energy to intermolecular form of energy, for example if 2 fluid layers are rubbing together, rubbing with respect to each other, then there is some heat that is generated. Just like if we rub our pumps, we see that our pumps get heated. So there is a change in internal energy. So there is an irreversible conversion of mechanical energy into intermolecular form of energy, and that irreversible conversion along with some heat transfer across the pipe, all these effects are accumulated in the form of this head loss. So this equation, although elusively looks like a Bernoulli's equation, and in many books it is written as modified Bernoulli's equation, it has actually nothing to do with the Bernoulli's equation. It is a energy conservation equation where the heat transfer, work done, all these effects are taken into consideration, and that culminates in the form of an equation which looks like the Bernoulli's equation, but instead of being applied across points it is applied between sections, and there is a head loss term to take into account the non-ideal effects which are not taken care of by the Bernoulli's equation. Okay, thank you. 1045.
Hello.
Hello.
Hello. Good evening.
Good evening.
We are very happy to get the information on Invicid flow, but Invicid flow is restricted to the ideal flow liquid. I want to know that whether this can be related to the real fluid. How come this Invicid flow can be correlated to the real fluid in terms of the boundary conditions and the restrictions?
Okay.
Is there any relevancy?
Yes, there is a lot of relevance. You have to keep in mind that whenever there is some topic in the text or in the course, it must have some practical relevance, because we are not doing mathematics course here, we are doing some real engineering exercise. And if you want to give a perspective, I will just give you a broad perspective, and the details will be covered by Professor Ghosh Maulik in the boundary layer theory. So the idea is like this: close to the wall viscous effects are important. As we move away from the wall, there is a region beyond which viscous effects are not important and velocity profile will not be developed. So that region which is outside an imaginary layer within which viscous effects are felt, in that region you can use considerations of inviscid flow. So considerations of inviscid flow cannot this need not be applied just for cases of fluids where the viscosity is 0, but effectively viscous effects are not felt. So, if you have a problem where boundary layer is formed, then within the boundary layer you solve the equations with viscous effects, but outside the boundary layer you solve the equations which do not take into account the viscous effects, and then you can match the solutions of the outer layer and the inner layer through some mathematics which will be covered in details by Professor Ghosh Moli.
Very kind of you, sir. Thank you.
Okay, thank you.
1263.
1263.
Good evening, sir.
Good evening.
First of all, two questions from yesterday's lecture. I have concluded from the yesterday's lecture that angular strain has no effect in the volumetric deformation. Is it true?
Yes, it is true, but again I am just reminding you that today's question answer session is restricted to dynamics of inviscid flows. Okay, we have
I have questions.
so please please try to ask questions on dynamics of inviscid flows in this session.
Okay. First of all, in the derivation of Euler's equation in the morning session,
Yes.
Before coming to the assumption of steady flow,
Yes.
You have in the left hand side equation you have considered that rad p dot dl, that quantity you have written as a dp.
Yes.
Okay.
Yes.
And you have considered that del p del x into dx plus d is equal to dp.
Yes.
But since we have not considered yet that steady flow, then why that del rho del p del t term did not change?
See.
And for v square also, that may also be function of.
See, in the governing equations, you have to keep in mind that in the governing equations where you are writing the force, the x component of equation is having a change in pressure due to x, y component of equation is having a change in pressure due to y, z component of the equation has a change in pressure due to z. So, the total change in pressure by considering these three components of the equation is a sum of the effect of change in pressure due to change in x, change in pressure due to change in y, and change in pressure due to change in z. This is true even if pressure is a function of time. Okay, this is a very important concept that you have to keep in mind. These are just the three components of pressure gradient that are coming into the picture because of the force balance along the three directions. So, there is no force balance in the time direction, that you have to keep in mind. Okay.
One very basic question.
Okay, okay.
Again, pertaining to the last lecture, that is regarding the two-dimensional flow concept. That is not clear to me actually. It's confusing. That suppose a velocity field is such that only u component is there.
Yes.
There is no v component or w component.
Yes.
But that u is function of x, y, and z. Is it a one-dimensional flow or not?
See, there is a little bit of like a finer distinction. There is a distinction between one dimensional flow and unidirectional flow. So, let us not go into this kind of very sophisticated distinction which may confuse you at this moment. We will come into the kind of velocity profile which you are talking about, where you have only one velocity component, but that velocity component is a function of a different coordinate. Like we will discuss about fully developed flow through the circular pipe or fully developed flow between parallel plates. These are called as unidirectional flow, and we will discuss about these flows in much more details when we come into the exact solution of the Navier-Stokes equation.
In this regard, I just want to ask that in the entrance region of a pipe, when it is not fully developed, at that time in the polar coordinate, the only axial velocity, that is function of both radial and the axial direction.
Yes.
In the entrance region.
Yes, yes.
But there is no v theta or vr component, right? in this case it will be treated as two-dimensional flow. But V theta or Vz component, Vr component is not there.
See, when we talk about I mean let us keep it simple. When we talk about one dimensional, two dimensional or three dimensional, we by one dimensional we essentially mean that we have only one velocity component, it may be function of whatever. The by two dimensional we mean there are two velocity components, and by three dimensional we are meaning three velocity components, that is the standard definition. So, we will adhere to that standard definition. But what happens in the entrance region of a pipe flow and all this we will discuss in details. Please wait till we come to that that stage of our discussion. Okay, thank you very much.
Okay, thank you, sir. Thank you.
1270.
1270.
नहीं है सर, कोई कोई दिक्कत नहीं है सर।
জিজ্ঞাসা করছে ডাউট আছে সবাইকে ধরে ধরে Oh, we will get back to you. You are not decided. 1235.
Sir, good evening.
Good evening.
Hello.
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 Am I audible, sir?
Yes, you are audible.
Hello.
Yes, you are audible.
Sir, good evening. Sir, good evening. Sir, my question is to Professor Goswami, sir.
Okay.
Sir, in the morning you were told for calculating the coefficient of discharge in a flow machine device, we need to conduct an uncertainty analysis. My question is how to do the uncertainty analysis in a flow machine devices, and what are the factors influencing uncertainty in flow machine?
No, I did not say that coefficient of discharge is related to uncertainty. You have misunderstood. I said that you have to conduct experiments to calibrate the instrument and find out the actual flow rate. What I mentioned about the uncertainty is a different thing. What I said was that in any measurement, the larger the value you are measuring, the less will be the relative error. So, for example, if you find that the manometer deflection is say 1 centimeter and the least count of your scale is 1 millimeter, then the uncertainty is 1 upon 10. On the other hand, if it is say 50 centimeters, then it will be 1 by 50. So, you want that HM should be larger, as large as possible. So, if you are going to measure the flow rate of say air at low Mach numbers, which can be treated as an incompressible flow, then you would prefer to use an orifice meter rather than a venturi meter. The reason being that because of the sudden change, sudden obstruction, the pressure drops in a orifice meter for the same flow rate will be higher. So, your HM will be higher. So, you will have more accurate results. That is what I meant.
Sir, excuse me. Another question, sir. Hello.
Yeah, please go ahead.
Sir, in orifice meter, how can we minimize the term vena contracta?
I didn't get your question. You have no
In orifice meter, in orifice meter, how do we minimize vena contracta?
You cannot minimize it.
How can we measure the vena contracta, sir?
No, you cannot measure it. See, you would like to have the pressure tap, downstream pressure tap as close to the vena contractor as possible, because then the curvature of the streamlines will not affect your measurement. However, that will depend on the Reynolds number, and you cannot really put it exactly at the vena contractor, because you are going to use a device for measuring flows of different flow rates, and you can't keep shifting it.
1241.
Hello.
Hello.
Good afternoon. Myself P.Q. Patel from NRI Group.
Okay.
Sir, my question is that the fluid is flowing in the room temperature. The continuity equation and Bernoulli equation can apply in the room temperature. If the temperature will be increased, then what will be the assumptions take place over here? And it will the Bernoulli equations are not satisfied over there if the temperature are increased. So which type of equation and which type of assumption take place when the temperature will be increased?
See, in the Bernoulli's equation we are only considering the mechanical energy. You have to keep in mind, in the Bernoulli's equation we are considering only mechanical energy. If we are considering the thermal interactions also, instead of using the Bernoulli's equation we have to use the first law of thermodynamics, and then you have to write an energy balance by considering the first law of thermodynamics involving the heat and work interactions. And for a reversible process you can combine that with some considerations of the second law of thermodynamics, and then you will get an equation which is again an energy equation which looks like the Bernoulli's equation, but there are certain additional restrictions, like you have to consider the process to be reversible, and it can be any reversible process for which you can apply this equation. But that equation is not the Bernoulli's equation, looks like the Bernoulli's equation, but it has to be derived when heat transfer effects are there. It has to be derived from more fundamental considerations of first law of thermodynamics and not just mechanical energy conservation, which is the hallmark of the Bernoulli's equation.
Sir, there is one more question. I am Professor Khabia from NRI Group of Institutions, Bhopal.
Hello.
And for flow measurement through pipes, we have different instruments like venturimeter and orifice meter and rotameter and so on. Now, what I feel while doing experiments is installing this device for flow measurement will itself change the value of discharge. So, how we account that error? Are you hearing me, sir?
Yes, yes. yes.
Well, you cannot help it. What you are trying to say is that the pressure drops will change if you insert the device, is it?
Yeah. What I feel is that when we install an orifice meter for flow measurement, the installation of orifice meter will itself change the value of flow. It will reduce the value of flow. Definitely, if we go for a venturi meter, then the reduction in the value of flow will be less. Maybe rotameter may have some medium effect. What we want is that when we want to measure discharge through a pipe, and we should have something which will cause minimum change in the actual value of discharge. After installation of the device for measuring discharge, if the value of discharge changes, then how we will get the correct value?
Now see, it depends on the circumstances. If you have fully developed flow, then the pressure gradient might already have been fixed, and then the flow rate may not change. Now, if you are doing experiments, then you want to get the experimental data at a certain flow rate. So, even if you have the flow meter, it is not going to affect the other measurements. So, for the flow rate which is read by your instrument, you can take your other data.
Another question, in the measurement of the flow in mass flow rate and their volume flow rate, why the diverging part are the long compared to converging part in the venturimeter?
Okay, so this is a question related to boundaryless separation. So, as I mentioned in my lecture, we will address this issue when we talk about boundaryless theory. See, what happens is that the pressure distribution is determined largely by the behavior of the flow in the core region of the duct, which behaves like an inviscid fluid. Now what happens is that you have a, what is called a favorable pressure gradient in the converging duct. That is, in the flow direction, because the area is reducing, the velocity will increase and the pressure will decrease. So the pressure gradient, sign of the pressure gradient is positive, dp dx, if you say x is the streamwise direction. Now the reverse happens in the diverging part for constant density flows. So as you move downstream in the diverging section, the area increases and the velocity decreases, hence the pressure decreases. So there the pressure on the downstream side is higher, it increases, and that produces gives rise to a net force on the fluid particle which is in the direction opposite to the flow direction, and that may lead to reverse flow near the walls. So you want to avoid that. Now regarding your previous question, I can make another comment. If you want, there is another way of finding the flow rate, that is, you measure the velocity at different points in the cross section. Now that also can be done in various ways. If you insert a pitot tube, again you can say that the flow might be disturbed, but if you measure it with, say, LDV, laser Doppler velocimeter, then by integrating the velocity profile over the cross section, you can also find the flow rate.
And my question is, sir, as the Earth can be assumed as a continuum of the control volume in context of the universe, so it may be possible that we can understand the values of the properties of the Earth by using a transport flow.
This is a question on Reynolds transport theorem, so this will be addressed by Professor Shom. Okay, we will take more questions from other centers.
Sir, thank you very much, sir.
Thank you. 1161.
Sir, good evening, sir.
Good evening.
Sir, my question is, the coefficient of discharge of HV meter is greater than coefficient of discharge of Orpus meter in case of water, sir. Whereas for air, it is reverse case, sir. Why it is, sir?
See, the coefficient of discharge will, if for incompressible flows, will depend only on the Reynolds number for a given geometry, and the Reynolds number combines the effect of the fluid properties and the fluid velocity in it. So now if you look at flow of air at high Mach numbers, then it will also be a function of the Mach number. So here for incompressible flows, whether it is air or water, it does not matter. If you calculate the Reynolds number and plot Ct versus Re, all the data points will collapse into a single curve if it is incompressible flow.
Okay, sir. One more question, sir. Sir, what are the practical applications of Reynolds transport theorem, sir?
Well, again this chapter has been handled by Professor Shom, but Reynolds transport theorem, first of all you have to understand that why this Reynolds transport theorem is necessary. We require conservation laws to explain the working principles of practical devices, like for example motion of a rocket. So motion of a rocket can be analyzed by using the linear momentum conservation, but linear momentum conservation or angular momentum conservation or mass conservation, these are routinely explained by referring to the concept of a control mass system, where you have some identified mass. Now in fluid mechanics we write, or we are comfortable in writing equations of motion with respect to control volume. So equations of not just equations of momentum, even equation of conservation of energy we want to write in terms of control volume. So there must be a transformational law that transforms the mathematical equations for a system, for a control mass system, to a control volume system, and Reynolds transport theorem precisely does that.
Sir, another question, sir. During the morning session, the thermal stratification,
Yes.
they said the lighter fluid and heavier fluid, the layers will be formed because of the lighter fluid and heavier fluids, or is it because of the thermal gradient between them?
No, no, the density gradient because of temperature creates the stratification. Okay, thank you very much. We come to a new center.
Thank you, sir.
1005. 1005. বক্স করে মুখটা দেখাচ্ছে you are not audible, you are not audible. 1177. 1177. Yeah.
West University. Can you please distinguish the free vortex and forced vortex flow, as well the application of Bernoulli's equation theorem on a forced vortex flow?
Okay.
How it can be applied?
Okay. So you have to like the first question is what is the difference between free vortex and forced vortex. I think Professor Som has discussed it in length, but just to recapitulate, V theta equal to C by R. So what is a vortex flow? A vortex flow is a flow where you have V theta component which is a function of the radial coordinate and VR equal to 0. So V theta equal to C by R and VR equal to 0. So this is the free vortex, and forced vortex V theta equal to CR and VR equal to 0. So this is the difference between the free vortex and the forced vortex. That is the answer to your first question. The answer to your second question, like it can be shown that the free vortex flow is an irrotational flow. So you can apply the Bernoulli's equation in a free vortex flow between any two points in the flow field, no matter whether they are located along the same streamline or not, provided other conditions of the Bernoulli's equations are satisfied, but the same thing you cannot do for a forced vortex. Okay, thank you very much.
One more question, please.
Okay, yes, yes, yes.
Good evening, sir.
Good evening.
How the invisible flow differ from compressible flow, sir? And one more question, sir.
No, I could not get your question. Please repeat your question. What is
how the invisible flow differs from the compressible
invisible flow? There is no, all flows are visible. There is nothing called as invisible flow. Possibly what you are trying to mean is inviscid flow, right? Is that true?
Inviscid.
Okay, inviscid flow. Inviscid flow and incompressible flow. Okay.
Yes, sir.
Okay, I mean they are two different things. They are two different things. Inviscid flow talks about viscous effects and incompressible flow talks about incompressibility effects. So incompressible flow means there is no compressibility effect in the flow, and inviscid flow means there is no viscous effect in the flow.
Okay, sir. Thank you, sir.
Okay. 1265. You are not audible. Yeah, please be louder.
I want to know what is timeline.
So, this flow visualization was discussed by Professor Som. So, it is better whenever. So, I mean timeline is essentially just like streamline, streak line, path line, another line for flow visualization, but because today's question answer session is restricted to dynamics of Invicid flows, we will take up only questions from that, and when tomorrow Professor Som comes back for his question answer session, please address this question to him. 1133.
Hello.
Yes, hello.
Sir.
Good afternoon.
My question is, in case of venturimeter, why the downstream angle is much more larger than the upstream angle?
Well, this question I answered just a few minutes ago. You want to avoid flow separation in the downstream section. So, if the angle of divergence is large, you will have flow separation and the pressure drop will be large. Why you will have flow separation, that will be discussed in when we talk about boundary layer theory.
Okay.
1133. Oh, okay. 1303. 1303.
Hello, sir.
Yeah, hello.
Hello, sir.
Yes.
Sir, I am still not clear with the static pressure, sir. What is the parameter that affects the static pressure, sir? Is it any relation with hydrostatic pressure, sir?
Professor Gosmolik will address this.
Well, earlier we talked about pressure in this course, and static pressure is nothing but that. See, we have now introduced another concept which we call stagnation pressure, and to distinguish this pressure or to emphasize that this is different from stagnation pressure, we are using the term static pressure. Now, you may have heard of thermodynamic pressure, that is a different issue.
Sir, excuse me, sir.
Yeah.
Sir, in the pipe, we will use a piezometer, that we will simply keep a pipe to measure the static pressure. Now, is it the hydrostatic is added with that pressure? Because we can keep the pipe upper side of the pipe or the lower side of that. Piezometer can be placed at the uppermost part and lower part also. So, with the static pressure, hydrostatic pressure is added with it, sir.
Now, I did not talk about this concept of piezometric pressure. Maybe in my next lecture I will talk about it. After that, you can ask me the question.
Sir, one more question. Sir, one more question.
Sir, is there an instrument named Pitot static tube and the Pitot dynamic tube?
Pardon?
If there are instruments named Pitot static tube is there in the textbook. Is there any instrument named Pitot dynamic tube?
No, you have a pitot tube and a pitot static tube.
What are saying? Pitot tube, Pitot static tube.
No, pitot tube and pitot static tube are different.
The Pitot tube is Pitot static tube.
We have today discussed the principle of the pitot tube. Now, I have not talked about the pitot static tube. Maybe I will discuss it as applications of potential flow after we cover potential flow.
Okay, sir. Okay, thank you.
1223. 1223.
I am PK Chaturvedi, engineering technical chamber. Sir, I want to know what is the difference between fully developed flow and the potential flow.
Again, there is no relationship between fully developed flow and potential flow. So, fully developed flow, when like if you consider flow through a pipe, the axial velocity component doesn't be I mean it remains a function of the radial coordinate only and doesn't become doesn't remain anymore the function of the axial coordinate. So, that is fully developed flow through a pipe as an example. There is a more general definition of fully developed flow, but I am not going into that for simplicity. So, if x is the axial coordinate and u is the velocity component along x, then u is a function of r only or y only, and it is not a function of x anymore, that is fully developed flow. And potential flow is irrotational plus inviscid flow. So, if you have an irrotational flow, it will remain irrotational forever if viscous effects are not present, if viscous dissipation is not present. So, inviscid plus irrotational flow together is called as potential flow. So, there is actually no correlation between, I mean these are just two different unrelated terminologies.
One more, sir.
Yes.
Actually, in inertial flow, there are two terms. One is temporal, another is connective flow.
Yes.
So, what is the difference between these and please make clear this concrete example, physical concrete.
So, you let me draw a schematic. Let us say you have a flow field like this. So, in this flow field, if there is a fluid particle at 1 and then the fluid particle goes to a point 2, then what is the change in velocity of the fluid particle? At the same point 1, if the fluid particle had remained, then because of change in velocity at the point 1, there would have been a del u del t. So, at a given location there could be a change in u due to change in time, but by the time the particle has come to a new location 2 where it finds a new velocity, because it has come to a new location where the velocity field is different. So, there is a component of acceleration, I am just writing one term, u del x. I am not writing the other terms because this is because of advection of the particle. With time the particle has come to a new location, at the new location it finds a different flow field, and therefore there is a change in velocity of the particle. So, the change in velocity of the particle is a combined effect of change in velocity at a given position due to change in time, that is the temporal component, and because of the change in position the particle finds a new velocity field, and that is because of advection of the particle, and that is called as the convective component, and the total acceleration is the sum total of these two effects.
Okay, sir, thank you.
Okay. One three zero eight.
Hello.
Hello.
Good evening, sir.
Good evening.
Good evening, sir.
Good evening.
Is it audible, sir?
Yes, you are audible.
Hello.
Yes, you are audible.
Hello. Question is, sir, in the morning section it was told that when it was about the venturimeter, that the measuring one end of the measuring tube is connected to the throat part and other end is connected to the just before the converging part. Why is it like this? Why not in the converging part? Why is it like this?
Alright, I will have to draw a figure and show it. See, look at the streamline pattern. This is inviscid flow. You will have a central streamline which will be horizontal like this. Now, this wall also is a streamline. So, you will have streamlines which go like this. Now, there is a streamline curvature here. So, if you put a pressure tap somewhere here, if you want to difference the pressure between this point and let us say suppose this is a manometer liquid level over here and this point, you have to also account for the centrifugal term due to the curvature of the streamlines, which you do not know, so you cannot estimate it. Now, we have been applying the hydrostatic formula that the pressure increases linearly with depth in the vertical direction. Now, that is true when the fluid is flowing also, provided that the streamlines here are horizontal. So, if you look at the streamline pattern, upstream here the streamlines will be, for inviscid flow, will be parallel. So, you would like to put the tap somewhere here, so that in this vertical direction you can apply the hydrostatic formula. Here if you want to apply it, there will be a significant error because of the curvature of the streamlines.
Thank you, sir.
1238. 1238.
So my question is that in case of the slurry, that is the mixture of the cement and water, how we can determine the viscosity? Because in that case, as the time progress, there is a change in the viscosity. So how we can determine the viscosity in that case?
Again, this is not a subject of today's discussion, but we can say that there are your question belongs to a specialized topic altogether known as rheology. So, in rheology there are devices which are called as rheometers, which can also determine the effective viscosities not just for time independent fluids, but also time dependent fluids. The fluids which have apparent viscosity as functions of time have special names, such as thixotropic fluid, rheopectic fluid, like that, and these are very complex fluids. And what I would like to tell you is that, see, this course, we please try to make use of this course properly. We have designed this course for the benefit of the fundamental understanding that you can provide to your undergraduate students. So, while there can be n number of questions from the area of fluid mechanics, you must keep in mind that please ask that kind of questions which will help you to explain fundamental concepts to your undergraduate students. That should be the motivation. I mean, of course, there are ways of measuring apparent viscosities of various fluids, and I mean there are devices and there are details of these devices, but this is not the correct forum to discuss about that.
There is one more question, that why the cyclones and anticyclones are always circular in nature?
Circular in nature, by that what you mean?
Then when they move in the circular path. The locus is circular.
Now I ask you one question, can you tell from which chapter, from which concept, from which chapter is related to the answer to this question? Is it, I am giving you some hint, is it related to force vortex or something like that?
It is you can say the general observation that the we experience is that.
No, there are, as I told you, there are many general observations and there are many ways of explaining general observations, but this session, please try to make use of this session. This session is for dynamics of inviscid flows. So there are several things that we observe in nature, and if we go on asking question that why this thing is observed and why that thing is observed, these are very important questions, but those are not related to dynamics of inviscid flows. So please restrict your question to the topic of dynamics of inviscid flows, because there are so many remote centers and we are addressing one remote center by sacrificing the question from the other remote center. They may be having more relevant question to the topic that we are discussing. So we do not want to make an injustice to the topic. So if you cannot restrict your question to a specific the specific topic for which the tutorial session is intended. I would say that for a more general question which is not related to these topics, please write emails to us and we will respond to those emails, but do not address that in a session which is intended for a particular topic.
Thanks, sir.
Okay. 1054.
Sir?
You are not audible.
Sir?
You
Hello, sir?
Yes, yes.
Sir? Hello, sir?
Yes, please go ahead.
Hello, sir?
Yes,
sir.
please
Sir,
please go ahead.
my question is, sir?
Yes, please go ahead. One three three eight. 1338. Yes.
My question is, why the length of converging and diverging part are not same in Venturi meter?
Okay.
I didn't get your question. Can you repeat it, please? Can you repeat your question, please?
There is a noise coming from your voice. Could you please look into that?
In Venturi meter, why the length and angle of converging and diverging parts are not same?
See, this question has been asked twice already and I have given the answer.
Next. 1317. 1317.
Good evening, sir.
Good evening.
Yes, good evening, sir. I have three questions. Two questions for Professor Suman, sir. Why stream function size not defined for three-dimensional case? You have defined only for two-dimensional case, but the potential function phi is being defined for three-dimensional. And another question, whether we can apply the Bernoulli equation for compressible flow like gas flow.
Okay, let me answer your let me answer these two questions, then you will address your question, third question possibly to Professor Ghosumouli. So my answer to the first question I have told yesterday. Again I am repeating, although we must keep in mind that this particular session is for dynamics of inviscid flows only, but I am answering very briefly. You have to define the stream function in a way that it satisfies the continuity equation. We have seen that the way in which we have defined the stream function, it satisfies the two dimensional incompressible flow version of the stream function only, and that is why that definition is valid for two dimensional incompressible flow, because it satisfies the continuity equation for two dimensional incompressible flow. It is not designed to satisfy the continuity equation for a three dimensional flow. However, the velocity potential, that definition is valid when the flow is irrotational, no matter whether the flow is two dimensional or three dimensional. So for an irrotational flow, we can see that the velocity vector can be written as a gradient of a scalar function phi for an irrotational flow. So that is valid no matter whether the flow is two dimensional or three dimensional, and therefore we can apply the concept of velocity potential not just for two dimensional flow but also for three dimensional flow. This is the answer to your first question.
So stream function cannot be defined in three-dimensional.
I discussed about this, that for three dimensional flow you can take projections of the flow on various planes and define artificial functions, but you cannot define a function, a parametric function that will automatically satisfy the three dimensional version of the continuity equation. So that is the answer to the first question. The answer to the second question, the look into the derivation of the Bernoulli's equation. In the derivation of the Bernoulli's equation we have integrated dp by rho, we have for that we have taken 1 by rho out of the integral. So it becomes 1 by rho into integral of dp. So that derivation essentially means that density, the rho is not a function of p. So that clearly shows that because rho is not a function of p, we cannot use that the Bernoulli's equation for an incompressible for a compressible fluid. So these are the answers to your two questions. If
So
you
for gas flow through pipeline, we can't apply the Bernoulli equation.
it depends on whether compressibility effects are important or not. If compressibility effects are important, you cannot.
Okay, sir.
Okay.
The next question, sir, whenever the flow through sharp edges or ellipses, why the vena contracta formation takes place?
Alright, the solid has a solid surface has a restraining effect on the flow. For viscous flows, the velocity at the solid surface which is stationary is 0, and the fluid particles close to the solid boundary has a velocity which is not very high, because it varies continuously. Now when you have a sharp orifice, as the fluid is flowing through it, that restraint of the wall is suddenly gone. So the fluid accelerates. So when the fluid accelerates and the volume flow rate is the same of the jet, there will be a contraction. That is one way to explain it.
Okay, sir, thank you.
1312.
Sir, good evening. We are from DMA College of Engineering 1312.
Yes.
I have only two questions, sir. All the flow measurement instruments like a pitot benchurimeter, orifice meter, the pressure tags are considered when the streamlines are straight. Just I like to confirm, is it correct, sir?
See, if you want to use the hydrostatic formula in the direction normal to the streamlines, then the streamlines have to be straight lines. If there is a curvature, finite curvature, then you have to account for the centrifugal force when calculating the difference of stream functions. That cannot be estimated because it depends on the velocities. So you want to put the pressure tabs
Thank you.
1178.
Hello, sir. Am I audible?
Yes, you are audible.
Sir, my question is, do all time it is true that for all fluid pressure is maximum at stagnation?
Can you repeat your question?
Yes, sir.
Yeah.
Do all time it is true that for all fluid pressure is maximum at stagnation? Stagnation point.
Yeah, pressure will be maximum at the stagnation point.
And one more thing, sir. I am little bit confused with inviscid fluid. That inviscid fluid exists and applicable.
No, there is no fluid which is inviscid. It is an idealization. But it does not violate the second law of thermodynamics. You cannot have a fluid with negative viscosity. A fluid with negative viscosity will violate the second law. A fluid with zero viscosity will, all processes in a fluid with zero viscosity will be reversible processes.
Okay, thank you.
1089.
Good evening, sir.
Good evening.
Good evening, sir.
Good evening.
Sir, my question is, you have derived Euler's equation of motion in the morning.
Yes.
In that, you have considered a control volume.
Yes.
You have analyzed the summation of forces in the x direction equal to mass times the acceleration in x direction. Out of that, you have added surface forces and body forces.
Yes.
In body forces, you have considered only positive x direction. Is there body force existing in the negative direction? If not, why it is not, sir? My question.
See, when you are considering a force, say you have one force of 10 Newton along positive x direction and a force of 4 Newton along negative x direction. So, what is the resultant force? So, 10 Newton along positive x and 4 Newton along negative x, the resultant is 10 minus 4 equal to 6 Newton along positive x. So, you will have along x direction either force along positive x or along negative x. By a sign convention, we are taking the force along positive x. If there is some force along negative x, we can represent the same algebraic expression with a negative sign. Okay. 1316.
Yes, good evening, sir.
Good evening.
Hello.
Yeah, good evening.
Am I audible, sir?
Yes, you are audible.
Sir, my question is practically where we can apply stagnation point, sir. Hello.
Can you repeat the question, please?
Yes, sir. The question is practically where we can apply stagnation point, sir.
No, why do you want to apply stagnation point? I don't understand the meaning of your question.
Where we can apply practically stagnation point, sir.
No, stagnation point may occur at certain points on a body.
Yeah, stagnation point is the point where the streamline intersect. There the velocity will be 0, sir. But in practically where we can apply, sir.
You mean in practice where it occurs? Yeah. I give you one example, flow over a cylinder. If you want, I can draw it again. So let us say you have a solid cylinder and there is a uniform flow. So this is a cylinder in cross flow. You may have a streamline which comes like this and hits the wall here. Now this streamline has a slope of 0 here. Now the wall is also a streamline because it is impermeable, and you have another streamline perpendicular to it. This tangent is at right angles to this. So this is a stagnation point, and if you consider inviscid flow, the fluid velocity along the surface may be non-zero, but at this point it will be 0. Otherwise there will be two tangents. Okay. So this is an example of a stagnation point.
Sir, my other question is that, is there any advantage between Venturi meter over Petri tube, sir?
Now Petri tube you use to measure the velocity, and the Venturi meter you are using to find the flow rate directly. Of course, what you can do is, if you have a fully developed flow in a duct, you can traverse the Petri tube and find the velocity at different points along the section, and in some cases you may be able to carry out a integration either using a numerical method or a graphical method and find the volume flow rate, but then you have to put in that additional effort. Whereas here in the case of the Venturi meter, it's a simple measurement, and using that relation you can find the volume flow rate. But of course, as I mentioned, you need to know what is the coefficient of discharge. So if the Reynolds number is large, that will be a constant. If the Reynolds number is low, that may not be a constant, and then you may have to iterate to find the flow rate.
Okay, okay.
1020.
Hello, good afternoon, sir.
Good afternoon.
So my question is, how can we find the direction of flow in a pipe by using the Bernoulli's equation?
See, Bernoulli's equation does not have any sense of directionality, because it talks about energies. So like if you have a velocity, and if you are interested to find out the velocity vector, then that velocity vector will have some direction, but Bernoulli's equation contains v square. I will reframe your question, and I have understood actually what you want to mean. What you want to mean is possibly that if you have two sections 1 and 2, and if you know the values of pressure, velocity and height, from that can you conclude whether the fluid is flowing from 1 to 2 or from 2 to 1? I think that is the question that you are asking. So if that is the question, you have to first calculate, as I told you, this is, you have to refer to not the Bernoulli's equation but mechanical energy conservation equation. So you have to calculate the sum total of P by rho g plus V square by 2g plus z at the 2 points 1 and 2. So the fluid will flow always from higher head to lower head. Remember one thing, that there is a misconception that fluid always flows from higher pressure to lower pressure. Actually fluid always flows from higher mechanical energy to lower mechanical energy, so higher head to lower head. So out of the two sections 1 and 2, whichever will have higher head, fluid will flow from that towards the direction of the lower head, because in the process it will incur some losses, so that will give rise to a decrease in head. Okay, thank you.
Sir, in addition to this question, hello?
Yes.
In addition to this question, shall we consider the total head, or shall we consider only the summation of static pressure head and potential head, which is also known as piezometric pressure head?
No, you have to consider the total head. Many times from the total head the V square by 2g term gets cancelled as you find out the difference between the heads 1 and 2, because at the 2 points 1 and 2, if you calculate the total head, maybe V1 square by 2g and V2 square by 2g are the same, so they get cancelled. So then it becomes the difference of the piezometric head, but fundamentally it is the total head and not the piezometric head just.
Okay sir. So one more question. So are the diameters of the pitot tube and the manometer tube same or different? If they are same, what should be the optimum diameter of the pitot tube for stagnation point to be achieved, and capillary effects on the manometer tube to be avoided?
No, the pitot tube, I do not know of any method to find the optimum diameter. You will be obviously obstructing the flow if you insert a pitot tube, and it should not be a very large diameter.
Okay, we will take the last question of the day before we come to a closure of the session. 1120.
Hello.
Yes.
How do surface forces arise in the movement, in the momentum analysis of controlled volume, sir?
Okay, this was addressed by Professor Som, but I would, I mean, we may respond to this question. So surface forces, there are two types of surface forces. One is a normal force, another is a tangential force. So you represent the surface force in terms of the normal component of the force and the tangential component of the force. The normal component of force, one part of the normal component of the force may be there even when viscous effects are not present, and that is because of pressure in the fluid, and when viscous effects are present, there is an additional component of normal force because of the volumetric strain in the fluid. So that is the normal component of force. The shear component of force is because of viscous effects in the fluid. So there can be normal components of forces and tangential component of forces because of the pressure distribution around the surface as well as because of viscous effects. There could be several other types of body forces in addition to the surface forces that we have mentioned, and the one example is due to gravity, but there could be several other examples of body forces. Okay. So thank you very much. I believe we have like interacted nicely in this over this session, and it has been an enriching experience for all concerned, and so we come to a closer to the day. Tomorrow we will have the first lecture by Professor Som on Reynolds transport theorem, the continuation of the lecture that Professor Som delivered today, and that will be followed by lecture on dynamics of viscous flows, which will essentially be talking about the equations of motion for viscous flows, namely the Navier-Stokes equation. Thank you very much.